I had a request to work through problem 623 on the method of joints, so we'll pick up here and go through that. So we have the drawing or the sketch of what that looks like here. Oh, here we are. So we have our frame or our truss here. We have some load P acting at point C in the downward direction. We have these distances D and D over 2. So let's get started here. So step 1, I'm going to find angles theta and phi. So I'm going to call this phi, and then a dashed line through the middle here. I'm going to call that half angle theta. Alright, so that'll be my first step. My second step will be find reactions at A and E. So taking equilibrium of the whole truss, what are the reaction forces at E, what are the reaction forces at A, and then we can use those in our method of joints. And then 3, use method of joints to find tensions. So we'll have to do that at multiple joints, perhaps all of them, perhaps only 4 of the 5, but we'll work our way through. So let's get started. So if we look here at, let's take theta, we know that this half is going to be D over 2. This length here is D. So step 1, find angles. With that information I can find theta. So tan of theta equals the opposite over the adjacent equals D over 2 over D. So our D's will cancel. So that's 1/2 theta equals arctan 1/2, which is 26.6 degrees. And then we can also do the same thing up here for phi. So our adjacent side here is going to be 3/2 D, so we have D plus D over 2, and then our opposite side is going to be D. So tan phi equals the opposite, so this D down here, so this length here is D again. This whole side is going to be 3/2 D. So it's going to be D over 3/2 D. Again, our D's will cancel. The 2 on the top will go, or on the bottom will go up to the top. Goes to 2/3. So arctan phi equals 2/3. Theta equals arctan of 2/3. I'll just make it tan to the -1. The -1 of 2/3. So phi equals 33.7 degrees. Alright, I'm doing that so I can find the components in relation to those. I could be doing tan, sine, theta, all of that with these D's, D over 2's, 3/2 D, but that's pretty easy to get confused in your head if you have an angle and you know what that angle is, and then you can refer back to that. Okay, that's cosine, that's sine of this angle. It's a little easier for me, at least, to keep straight in my head. So we've got step 1 done. Now we're going to find the reaction forces. So remember that the whole truss is in equilibrium. So that means that this force at point C, the force P here, has to be counteracted by some other forces at E and A. So at A, let's take a look at this. What kind of reaction can we have here? We have sliding contact, so we can only have something normal to this. So our normal at A is only in the x direction. and then at E here, I'll tip my hand a little bit, so if A has to be going this way, right? It can't really be pulling into the wall, so it must, at E, my reaction force at E in the X direction is going to be that way. And then if I'm pulling down here, I need to, at point C, I need to be pulling up some amount at Y to, at E in the Y direction to counter that P force in the negative Y direction. So how am I going to find what those values are? Well, we can do the sum of the X components has to be 0. We can also do sum of the Y components has to be 0. And we can also do the sum of the moments, and I'm going to pick around E has to be 0. And why did I pick E? Well, if we're only solving for our reaction forces, this creates a moment around E, this creates a moment around E, and I know this one, and I don't know these two, so since I picked E, these create no moment at E. So I have two unknowns there, but I can isolate those and only have one unknown, this normal force A, with my P creating moments. So let's start with that one. So the sum of the moments around E equals 0. So I'm going to have P times D, and what kind of moment is that going to create? Well, it's going to make clockwise rotation, so I'm going to have negative P D, and then at A I must have a positive, right? So I'm going to have plus my normal force at A, and what's the moment arm for that? It's going to be D plus D over 2 gets me to this A, so I'll just call that 3/2 D, and I have my equals 0 on that side, so I'm going to have PD equals NA 3/2 D. My D's can cancel out. Those are the same D. I should have both made them lowercase. So NA then, dividing both sides by, or multiplying both sides by 2 and dividing by 3, gets me 2/3 P for my reaction force at A. Alright, so there we go. Let's take the sum of the forces in X then. Sum of the forces in X equals 0. So I have 2/3 P plus, force at E in the X direction equals 0. Force in the X direction at E equals negative 2/3 P. So there's that part. So my X components cancel each other out, and then the sum of the forces in Y equals 0. So I have negative P plus force at E in the Y direction equals 0. It's pretty obviously then the reaction force in the Y direction at E equals P. So we have those three. Alright, so there's our reactions. So we can check that off, and now we'll do the method of joints. So we'll start at joint E. That's where we know the most amount of information, right? So we now know FEY and FEX. What we don't know is tension in CE. I'll call this CE. I'll call this DE. Here's CD. Here's BC. Here's BD. AB. and AD. Alright, so I don't know DE or CE for joint E. I do know FEY and FEX. So I will start at joint E and work from there. So this is step 3, right? Method of joints? Yep. Alright, so step 3, method of joints. So I'll start with joint E. I'm going to draw a free body diagram for that. So here's E. I've got, sorry, that went crazy on me. So I've got FEY here. I have FEX there. And I'm gonna assume everything is tension. So I'm going to be pulling on all my joints until I've proved otherwise that that's in compression. So if I find a negative sign, that means my force is the correct magnitude, but it goes in the opposite direction, meaning that member is in compression. So here's my, I think this was DE is down. I should have maybe drawn that on the other side. And then here's going to be CE on that side. And this again here is that phi. That kind of came out poorly. So let's start with what we don't know. So let's do sum of the forces in X. So we know this one. This has no X component. DE has no X component, so we just have CE. So taking that part, we can solve for CE, and then we can use that to find DE in relation with FEY and CE, and we can solve that. So in X, we have negative 2/3, that was bad, 2/3 P plus, what do we have here? So the component of CE in the X direction is going to be sine of, what was that, 33.7, and that's CE equals 0. So we'll find CE equals 2/3 P over sine of 33.7. So if I fill in numbers for that, I find CE equals 1.2 P. And since I have a positive sign here, that does mean that's in tension. So I'm going to write tension next to that. Alright, so there we've got one member down. Let's take a look at DE now. So sum of forces in Y equals 0. So what do we have? We have FEY minus, what is the component here of CE? It's going to be cosine 33.7 degrees CE. And then we're going to have minus DE equals 0. So we have, filling in the values now, we have, what do we have? We have P minus cosine of 33.7 times 1.2 P minus DE equals 0. I'm going to slide my DE to the other side. It's P minus 1.5 P cosine 33.7. And when I fill in values for that, cosine of 33.7 is going to be pretty close to 1. Turns out that DE equals 0. So it's a 0 force member. We couldn't tell that from our rules just looking at that. Sorry, zooming back up here, we had a reaction here, we have some load here. It's collinear with BD. You would think that that if there's one member coming off of that, that one member would be 0 force. In this case, none of those rules would have helped us figure out that DE is a 0 force member. So we did a little extra work to find that, but it wasn't wasted because there wasn't a way to determine that otherwise. So we're done with joint E. Let me zoom back up for a second. So we're done with joint E. Now we know CE. We know point P here. So let's move on to joint C, where we don't know CD or BC. We do know CE. We do know the load P. So then we can find CD and BC. That was a mouthful. All right, moving on to joint C. So joint C. What do we have here? Let's draw a little free body diagram of that. So we've got P coming down. We had CE was in tension, so it's going to be pulling on our joint. That's not quite the right angle, but we'll go with that. I'm going to assume this is in tension. This is CD, and this is CB, also assuming that's in tension. So that's our free body diagram of that joint. So what are, and then again, this is going to be our, this is theta, this is also theta. This one up here is, let's see, what do we have there? We've got, from horizontal, this is going to be 90 minus phi. But we could also look at that from cosine sine of our other angle there. So let's see, let's do, so we know two verticals. So let's do that component of things first. So sum of the forces in y equals 0. What do we have? We have negative p plus, what do we find for CE? For CE we had 1.5, 1.2, excuse me, p, and then what are we going to have there? We're going to have times the sine of 90 minus 33.7. This thing, we can make it into cosine of 33.7. Sine and cosine will be the inverses of each other there. And so that's those two things that we know. What we don't know is, so we'll have plus cosine of, what was our theta? Theta was 26.6 degrees. CD minus cosine 26.6 degrees BC. So this part is going down, this part's going up. That's the difference in sine, equals 0. So we'll fill in our values here. So we get negative p cosine of 33.7. That is, times 1.5 is positive p. So then we have, so those cancel each other out. So we just have cosine 26.6 degrees CD equals cosine 26.6 degrees BC. So it becomes pretty obvious then that CD equals BC. Alright, so then we can use sum over forces in X to find what that value is. So in the X direction, we're going to have negative sine of 33.7 degrees times 1.2 p. That's our CE component in the X direction right here. And then we're going to subtract off cosine 26.6 degrees BC minus cosine 26.6 degrees CD equals 0. So it's pretty obvious that one of these, or maybe both of them, are in compression. So we have all negative signs. So sine of 33.7 times 1.2, that gets us 0.6658 p. Now pretend I moved that on the right and flipped everything around. Equals, and since BC and CD are equal to each other, equals negative 2 cosine 26.6 degrees BC. So BC equals negative 0.6658 p over 2 cosine 26.6 degrees. If I do my math correctly there, I get 0.3723 p, and that's negative, so that gets me compression member. And that also equals BD, so I'll just put an equals, not BD, excuse me, CD. That also equals CD. Alright, so we've got, let's take a look at our sketch again. So we found CE, now we found CD, we found BC. Where should we go next? We also found DE, I guess. Let's go to joint B next. So we have this component that we know, we don't know this or this, so we can find those. We have two unknowns, we can have two equations of equilibrium. So look at AB and BD along with BC. So we're going to move to joint B. Joint B. So what do we have there? We've got this point down here, that's B. So we have BC we had is pushing on it. It's a compression member. So there's BC. We have BD. We don't know its sign yet, so I'm going to call that a tension member pulling on it. And AB we don't know, so I'm also going to make that a tension member. So we'll do the sum of the forces. I'm going to do X first, since this BD component has no X component to it. Sum of the forces in X equals 0. So we have negative cosine 26.6 degrees BC. That's that X component that would be acting here. And then we'll have negative AB cosine 26.6 degrees as well. So that's a symmetric triangle down there, equals 0. So we'll move AB to the other side. AB equals negative BC. So AB equals 0.3723 P, and that's also in compression. Alright, so we've got that, so we could actually switch that sign around. So it should be pushing in this way. So our sum of our forces in Y equals 0. So what do we have there? We have negative sine 26.6 degrees BC minus sine 26.6 degrees AB plus BD equals 0. So BD equals, and since AB and BC equal each other, we're going to have BD equals 2 sine 26.6 degrees AB. Filling in those values, we find BD is 0.3333 P, and that is a tension member since that came out to be a positive sign. Alright, so we've got that, and now last we can do joint A. So at joint A, what do we have going on? Here's our joint. We have this normal force, that reaction at NA. We had AB was in compression, so it's pushing on that joint. So we've got that force here. This is AB. We have AD here. And I'm going to assume that's a tension member. So what should we do first here? It doesn't really matter which one we do. We'll do the sum of the forces in X equals 0. Y might be a little faster, but I'll stick with the X. So what do we have here? We have NA minus cosine 26.6 degrees AB plus cosine 26.6 degrees AD equals 0. So what do we have then? NA, let me flip back to my first page. NA was 2/3 P, and this was negative cosine 26.6 degrees, and AB was 0.3723 P equals negative cosine 26.6 degrees AD. So if we divide this by negative cosine 26.6, that gets us our value. If I do my math there, I find AD equals negative 0.3723 P, so that's in compression. So I can get rid of that. Excuse me. So that was in compression. Oh, sorry. That was in compression. So I'll just get rid of that negative sign that I had in front there. So I'll get rid of that. Oh. So 0.03723 P in compression is AD. So that should finish us off. So to summarize what we did, came up here, we defined these angles just to make it a little easier in our equations to keep track of what quantities we were looking at. Then we found the reaction forces for the whole truss to be in equilibrium, and then we just started from there and marched our way around until we solved all the members. So we actually didn't solve joint D because we had solved those 3 members using other joints. So we did 4 methods of joints to solve the whole truss.